your video last night was over periodic trends. And we're going to discuss just some brief, I think I got about, what's it say, maybe 10 to 12 slides here to discuss the periodic trends and certain things that we will be using throughout the year with the periodic table. Some of them we use more than others. Electronegativity is something that keeps coming back and coming back and coming back. All right, so we will use those. Now, sometimes when we have periodic trends, I gave you that help sheet. Okay, I gave you that help sheet, but a lot of this stuff is on the periodic table. So go ahead and take your periodic tables out so we can take a peek at those too. But a lot of this information is on the periodic table also. As we talk about the periodic trends, we will be looking at a few of them. We'll be looking at the atomic radius. We will be looking at ionization energy, the electronegativity. And if you look at your chart, I have electronegativity, I have electron affinity. Your arrows for those two things should be identical, aren't they? They should be identical. So in this video, or this PowerPoint, I'm going to group those two things together, the electronegativity and the electron affinity. Reactivity, your overall reactivity of elements, and finally, the metallic character. So, as we are looking at the atomic radius, okay, it is the size of an atom, the distance from the nucleus to the outermost electron. Now, this value is, as I said on the video, this value is kind of hard to calculate. So the way that it's done, all right, the two elements are bonded together, okay? So let's say we have, we'll just use a halogen. Remember from yesterday, what group are the halogens? Group 17. So let's say we got a chlorine bonded together with another chlorine. You'll learn here in a couple weeks that that is a covalent bond. On that covalent bond, we will measure the distance from the two nuclei. Once we get that distance, we will divide that by 2, and it'll give us a value, the atomic radii. Now, as you can see with this diagram here, we are dealing with the main group elements. Once again, from yesterday's talk, what are the main group elements? What are the main group elements? If you can't spit this back to me, we need to look in our notes. What do you think? The S and P block. Good, Bree. The S and the P block. So we're just looking at the S and the P block right here in my diagram. But as it appears, where are the bigger atomic radii? Bottom left, correct? Looks to me like that's pretty big if these little spheres are the indications of the atomic radii. Okay? Looks pretty big here. Does that make sense? Does it make sense that it's bigger down there at the bottom? We got more electrons, don't we, down there? We got more protons. Yes. Makes a little bit of sense. So, as we are going down a group, the atomic radii is increasing. Okay? As you go down, the electrons are filled into orbitals that are farther away from the nucleus. The more electrons that there are, the farther they get from the nucleus, the less the attraction is. As we go across the period, from left to right, the atomic radii decreases. Okay? There are more electrons. Okay? There are more electrons, but on that same energy level, the attraction is greater. So the more electrons there, and they're on that energy level, they attract greater, thus they decrease the size. The ionization energy. The ionization energy. The energy that is needed to remove the outermost electron. Now look at this chart I have up there. Where is it hardest to remove electrons? With what group on your periodic table? What group on your periodic table is hardest to remove electrons? Fletcher? Non-metals. Give me a specific group. Be more specific than non-metals. Brandon? The noble gases. Excellent. Good, guys. Now, the noble gases do not want to lose electrons. Any idea why? Their outermost shell is completely filled. Remember, we talked with electron configurations. When we get to that P6, those P6s are full shells. Okay? If one of those noble gases lose an electron, is their shell filled? No. No. What group do you think would be really, really willing to dump an electron, to get rid of one? Yeah. Metals, specifically which ones? The alkali metals. Because they all have one on a new shell, don't they? If they dump one, then it goes back to that P6 almost like. You're going to see that when we talk about ions. When we talk about ions. So this ionization energy, the energy to remove electrons, it makes sense that non-metals probably don't want to remove electrons, do they? Metals, they probably want to get rid of them. So, as we go down a group, ionization energy decreases. Okay? As you go down, the atomic size is increasing. There is less attraction. Therefore, it is easier to remove electrons. The periodic trend. As we go across the period, we start with the metals. On the left and on the right are the nonmetals. So, ionization energy increases. And remember, ionization energy is the amount of energy to remove an electron. The metals want to get rid of electrons, so it'll be lower. The nonmetals do not, so ionization energy is higher with them. All right? Now here's a diagram. Okay? Here's a diagram, and if you look at these values, okay? You look at these values, the amount of energy to remove one electron from sodium is 495.8. Okay? Well, that makes sense because sodium has one electron on its valence level. Okay? Look how much energy it takes to remove that second electron. You know why? It gets rid of one electron, its outermost shell is filled. All right? Let's look at magnesium here. Magnesium is in group 2, the alkaline earth metals. So how many electrons does it have on its outermost energy level? 2. So does it make sense it wants to get rid of 2? Yes. Does it want to get rid of 3? No. So look at this. Get rid of 1, 700. 37.7. Get rid of 2, 1,451. But that third one, see the jump. See the jump. So if you look on these jumps, the reason being, okay, look at the electron configuration. Here's the S1, here's the S2. Here's the S2P1. So does it make sense that their outer wants to get rid of 3 of them? Yes. Electronegativity. I want you to find on your periodic table. Find on your periodic table values for electronegativity, because we use these babies a lot. So familiarize. It might be on the back. Okay, I don't know about the big periodic tables, because those are new ones. The electronegativity. It's on the back. It's in green, isn't it? Okay. It's an important one. They even put it on a different color. All right. Now, with electronegativity, the way that I remember this is I just remember what my greatest electronegativity is. Look right here. Fluorine. Fluorine right there. Check out fluorine's electronegativity. It is the highest. Okay? Fluorine has the highest electronegativity. My chart says 4.0. What does your chart say? 3.9. Okay? So, electronegativity is the tendency of an atom to attract electrons. Okay? To attract electrons. Now, the halogens. Look at the halogens on your periodic table. They are 1 electron away from filling the outermost shell. Correct? Does it make sense that the halogens want to attract electrons? They want to pull electrons in? Yeah, because they want to fill that outermost shell. That is why those halogens have high electronegativities. So, as we go across that table, they're getting bigger. Does it make sense that metals don't want to attract electrons? Look at sodium. We've been talking about sodium. Does sodium want to attract electrons? No, it wants to do what? Dump one, right? Does magnesium want to attract electrons? No, it wants to get rid of them. So, as we look at this electronegativity, and we can also say the electron affinity, okay, because they're pretty similar, like I said before. Group trends, as we go down a group, the electron affinity, thus the electronegativity decreases. The atomic size is increasing, so there is less attraction of electrons to the nucleus as we go down. As we go across the period from left to right, electron affinity, thus the electronegativity increases, and we discussed that. Okay? We discussed that. They want to attract electrons because they want to try to fill their outer shells. Reactivity. Reactivity is the tendency of an atom to react. All this discussion we've been having here today is talking about metals wanting to lose electrons. So, metals' reactivity is based on the lowest ionization energy that's in the bottom left corner. Okay? Low ionization energy equals high reactivity. Low ionization energy equals high reactivity. Stop and think. We watched a video yesterday on alkali metals, right? Which one blew up the glass? Cesium, right? Cesium blew up the glass. Where's that at? Bottom left of the table, right? Low ionization energy, high reactivity. Okay? Now, don't get me wrong. Don't get me wrong. Sodium and lithium, they're up top on the alkali metals. They're still very reactive, weren't they? We saw them spinning around in the water. But they didn't blow the container up, did they? So those are still highly reactive, but when we talk in terms of the most reactive. Nonmetals. Nonmetals want to gain electrons, as we've been discussing. Okay, so the reactivity is based on electronegativity. Who has the greatest electronegativity? Fluorine, right? So the place the metals are the most reactive is the upper right. Once again, all of the halogens are pretty reactive because they want to gain one electron. But the biggest hitter, the most reactive, is fluorine because it's got the highest electronegativity. So high electronegativity equals high reactivity when we're talking about nonmetals. When we're talking about metals, we look at low ionization energy. The lower ionization energy means the higher reactivity. Metallic character. The metallic character. As you go down a group, metallic character increases because ionization energy increases. As you go across the period from left to right, the metallic character decreases. Does that make sense? As you go left to right, the metallic character decreases. As you go left to right, you're going from metals to nonmetals, aren't you? Doesn't that make sense? That as we're getting towards the nonmetals, that the metallic character decreases? That makes sense to me. Does it to you? Just nod your head yes. Since it makes sense to me, just nod your head. Say, yeah, it does to you too. All right. Okay,